Hello again, and welcome to part 2 of the lecture for section 7.6 of intermediate algebra. If you'll recall last time in our first part of this 2-part lecture, we were looking at how we can solve problems associated with rational equations. We looked at how we could solve similar triangles, and we looked at how we could solve simple translations. And now for the work principle. The work principle is an interesting concept that we have to understand because you guys already have an understanding of it. Let me kind of try to direct that understanding so that we can tie that into what we're talking about today. Very simple. If it takes you 3 hours to knit a sweater, how much of that sweater can be done in 1 hour? Well, if it takes me 3 hours to knit the whole sweater, 1 hour, it's going to take, I'm going to have 1/3 of the sweater knitted. All right. Well, what if it takes you 6 hours to bore out the cylinders of your motor? All right. How much of the job can be done in 1 hour? 1/6, right? So with each of those, you took the one and you divided it by the total amount of time that it took you. So with the work principle, that's what we're considering here. All right? The work principle. If it takes A length of time to do a job. All right? Then 1/A can be done now. Then 1/A can be done in a single unit of time. Just what we talked about. If it takes 3 hours to knit a sweater, 1/3 of the job can be done in 1 hour. So what we're going to do now, is to understand that if it takes A length of time to do a job, then 1/A can be done in a single unit of time. The work principle is based on that. So what we have is A, whether it be Anne, Albert, Augustina, August, Anton, whatever. A can do a job in little a, length of time. B, whether it be Bob or Beulah or Becky or Betsy or Bertina, all right? Bertina can do the job in B, length of time. And T is the total time. Then we have the work principle. And the work principle says quite simply this. That 1/A plus 1/B equals 1/T. Now we've got a few examples that we're going to look at here. Some of them I've cut and pasted into the lecture. Others I'm going to refer to the text and write them out for you. So let's take a look at the first one that we're going to deal with. The first one we're going to deal with, using the work principle, is this one. An experienced roofer can roof a house in 26 hours. A beginner needs 39 hours to do the same job. Okay. How long will it take if the two roofers work together? Well, ladies and gentlemen, that's what we've got to understand when we're dealing with the work principle. We've got two situations, an experienced roofer and a beginning roofer. And I like this example because, you know, we've got an experienced roofer. We've got a beginning roofer. It kind of helps us to tie into the variables that we talked about a second ago. So the experienced guy, 26 hours alone. All right? The beginner, 39 hours alone. And the total, we don't know. So the total, we're going to declare a variable of t. So we plug this into the work principle. We have our experienced guy, A, which is 26. We have our beginner, which is B, 39. We have our total T. All right, so we don't know what that is. Now the problem is, with this, is we have to find an LCM. Now the reason we have to find an LCM, ladies and gentlemen, is that we have more than one ratio on each side. Cross products could be used if this were a single ratio over here, but if you'll notice, we have two ratios over here equaling the one over here. It's not a single ratio equals a single ratio. So we have to find our LCM, as we learned before. And our LCM, what we've got to do is find the common denominator for these two. Okay, the LCM. So we have 26 and 39. The 26 is 13 times 2, and the 39 is 13 times 3. So our LCM is going to be 13 times 2 times 3. Well, when we've got 13 times 2 times 3, what we're going to end up with is 78 as our LCM. Now the reason, again, that we want to use our LCM in this manner is it's easier to see what's, what we're going to cancel with. So we're going to take this entire equation here, and we're going to multiply both sides of this by the LCM, which is 78t. Now where did that t come from? Well, we've got to look at every denominator here. Every single denominator here. The 26 down here. The 26, the 39, and the t. The LCM of 26, 39, and t. Well, we found the LCM of the coefficients right here. But we've got to consider all the terms. So that's why we have the 78t there. So, doing this, we look at this. We got 26 cancels with the 78. I love using our LCM this way right here because, ladies and gentlemen, when we look at these three, that is what 78t is. 78t is that. So, by looking at it that way, when we multiply this, the 78t, by the 26, the 26 is the same as 13 times 2. So what's left is 3. 3 and the t. So we have 3t here. Again, we're multiplying this by 39. 1 over 39. 39 is the same as 13 times 3, so what's left is the 2t. And on the right-hand side, I hope you can see that what's simple enough is that the t's will cancel in this last product over here. So we end up with a 78. Well, what is it? Okay, now we have 5t equals 78. 5t equals 78. Which is going to give us 79/5 when we solve this. Well, 79/5. Okay, what's it going to be? We're going to end up with 15 here, because when we divide that out, 5 goes into 79 15 times 15 and 4/5 hours. Now, it's not going to be important for you to convert this into hours and minutes. That's fine right there. What you have is 15 4/5 hours. Now, what I want to do is I want to show you another example here. This one, since it comes directly from the text and doesn't allow me an opportunity to cut and paste, I'm going to write this down. What we have now is on number 52 of the text. It says one person proofreads a copy for a newspaper in 4 hours. If a second one is employed, the job can be done in 2.5 hours. How long does it take the second proofreader to do the job alone? All right, that's an interesting question, because when we look at how we solve equations, we can look at the first one, the first proofreader. The first proofreader does the job in 4 hours. The second proofreader, we don't know, so we declare it as a variable. The total, unlike our previous example, we do know the total. It's 2.5. Ladies and gentlemen, we don't like dealing with these mixed numbers, so we're 2.5. Well, let's hope we can all remember how to work this 2.5 out. You guys remember how to do 2.5? When we change 2.5, we look at the 2 times the 2, and we add the numerator to it. All right? So 2.5 is the same as 5 halves. Now, with this problem, it's kind of interesting because we're going to have the same setup that we had with the work principle a moment ago, but one of our 2 here is unknown. Now, and another thing about this problem that makes it interesting is that we're going to require you guys to remember fraction division. We've got 1 divided by 5 halves right here. And when you divide a number by a fraction, you flip it and multiply, don't you? So when we flip it and multiply, in other words, flip it and multiply means multiply by the reciprocal, we end up with 2/5. As an aside note, let's remember this, right? As an aside note, we have 1 divided by 5 halves, which is 1 times 2/5, which is 2/5. So this right, all this right here is how we came about this. Okay, so that's our little aside note there, and we're done with our aside note. So now, what are we going to do? Now we're going to simply look at our LCM, and our LCM with this one is 20x. So we multiply both sides of this equation by 20x. The 4 cancels with the 20x, giving us 5x. The x cancels with the 20x, giving us a 20. The 5 cancels with the 20x, giving us 4. x, but we still have that 2 out front there. So this 2 in the numerator, this 2 right here in this numerator is where this 2 right here comes from. And then the 5 canceled with the 20, and that's where the 4x came from. So after we've cleared the fractions, then we clear the parentheses. So we have 5x plus 20 equals 8x. And then we subtract the 5x from both sides, so we get 20 equals 3x. Dividing by 3, we now have 20 over 3. Strongly discourage you from grabbing your calculator and using a calculator to do this. Use fractions. 3 goes into 20 how many times? 3 goes into 26 times with 2 left over. So 6 2/3 hours. Now that, ladies and gentlemen, is the work principle. And the work principle, it's not, a friend of mine had mentioned to me one time whenever I called it the work principle, is that Newtonian physics? And I'm like, no, it's not Newton's work principle. It's simply the work principle to help you to understand how to solve work problems. Now, it's not always work problems, because you can actually use this to figure out if it takes you 20 minutes to eat a pizza and your friend 15 minutes to eat a pizza, how much can you guys eat together, and how much time would it take you to eat that one pizza together? So it's not just work, but I guess eating a pizza could be considered work because you're burning calories to eat. You can use the work principle to calculate length of time for conveyors, assembly lines, proofreaders, roofers, plumbers, pizza eating, sweater knitting, carburetor rebuilding. This work principle can be applied to all of those. All right. Now let's take a look at another. Let's take a look at how we can look at distance equals rate times time problems. I strongly encourage everyone here to use a table when you're solving the distance rate time problems. All right. When you do this, you're going to have situation A and situation B. You're going to put it into a table with distance, rate, and time. All right? When you set it up in a table like this, it's going to help you because all your information is consolidated in one nice place. So you're not having to go back and refer to your problem over and over and over again and read it over and over and over again. Yes, it's important for you to read your word problems at least more than once. And when you read word problems, don't read it as though it's a Field and Stream article or a Cosmo article. Read through it carefully. Look for key words like is, increased by, greater than, with the current, against a current. Look for all of those things. All right? When you're considering problems that involve currents, all right, if you're going with a current or against a current, these are all important things to look at. Now, when I say current, I'm talking not only rivers, but I'm talking air streams. So anytime, if you're ever going with the current, it's going to be your vessel rate, if you're going with the current, plus the current. Okay? If you're against, it's always the vessel minus the current. So those are important things to understand. All right. Also, if you're given distance, it's going to be your total minus the distance of one to equal the other, if you're ever given the total. Now, another thing to consider is this. All right? If you're asked to find the rate, R, then you will use T equals D over R. If you're asked to find the time, T you will use the R equals D over T. A lot of times this confuses students a little bit. So they're saying, you mean I'm using the T formula to find the R and the R formula to find the T? Yes, because of the way that substitution works out. And hopefully you'll remember way back to chapter 4 when we talked about substitution, all right, and elimination methods. By the substitution elimination method, to solve for X, we always jack with the Y, and to solve for Y, we always jack with the X. So when we're looking at these kinds of problems, when we use the rate formula, what ends up happening is through the process of substitution, we end up with only a T. So let's consider a problem. This is again a cut and paste problem, and I'm also going to include another one out of the text that I'm going to write out for you. The speed of Lazy River's current is 5 miles per hour. A boat travels 20 miles downstream in the same time as traveling 10 miles upstream. Find the speed of the boat in still water. Okay, so what we have is two situations here. Two situations. We have a downstream situation and we have an upstream situation. All right, so let's label that. We've got a downstream situation and an upstream situation. Now, there's one thing I dislike about the author is that the author uses the variable x over and over again in too many situations. When I'm dealing with distance, rate, and time, I always want to deal with a d, an r, and a t. So what we have here is a d, an r, and a t. We have us a nice little table from which we can that we can put our information into, and then we can use that table. Okay? So we have two situations here to deal with. The speed of the Lazy River's current is 5 miles per hour. Look back here. When we're dealing with currents, with the current, it's always the vessel rate plus the current rate. And against the current, it's the vessel minus the current. Do we know the speed of the vessel? We don't know the speed of the vessel. In fact, it's telling us right here that we're supposed to find the speed of the boat in still water. And the vessel is the boat. What is the distance downstream? The distance downstream is 20 miles. So there we can put that 20 in there. And the distance upstream is 20 miles. All right, see, there it is, 10 miles upstream. All right, now the speed of the current is 5. If I'm going downstream, in other words, with the current, then it's going to be my boat. I don't know what the rate of my boat is. Find the rate of the boat. So I'm going to call this R, because R is a rate. Downstream is plus, because I'm going with it, plus 5. Against, I'm going R minus 5. See, that's what that right there. The speed of the current is 5 miles per hour. Now, what about the time? Well, let's look at here. This is very important. In the same time as traveling, 10 miles per hour. So it travels 20 miles per hour, 20 miles in the same time it travels 10 miles. So the time for both of these guys is t. Now, what does it ask us to find in this whole deal? Upstream, downstream, the whole deal. What is it asking us to find in this? Well, what is it asking us to find here? Yeah. R plus 5, R minus 5, t time t. Well, there was something I messed up in here. Downstream and upstream. This right here shouldn't be there. It should be a 10. Right? It's asking us to find. What is it asking us to find? It's asking us to find the speed. Find R. Let's go back again. If it's asking us to find the rate R, we use T. Where do I get T from? Well, distance equals rate times time. Distance equals rate times time. So what is our downstream equation? Our downstream equation is T equals 20 over R plus 5. Our upstream equation is going to be T equals 10 over R minus 5. Now, a while ago, I asked you guys to remember way back to chapter 4 when we looked at substitution. Substitution is so important in every type of word problem. All right? If T equals this, and T also at the same time equals this, through the process of what we call substitution, now this is not discussed a lot in the text, but it's very important for us to understand. If T is this, and T is also this, all right? T is both those guys. If T is that, then what we can do is we can use substitution. T equals 20 over R plus 5, and T also equals 10 over R plus 5. What we can do is we can set those guys equal to each other. Oops. So that's what we're going to do. T is 20 over R plus 5, and T is also 10 over R minus 5. What's our LCM here? Oh, do we need to use the LCM? No, we don't. Why? Because we have a single ratio equals a single ratio. We can use cross products. We can use cross product. How can we use cross product? We couldn't use cross product in our work principle a moment ago because we had more than one fraction on each side. So we do a cross product, giving us 20. R minus 5 equals 10. R plus 5. Clearing our fractions, clearing our parentheses. That's what we have. Isolating our variable. What is the rate of our boat in still water? 15. 15 what? Miles per hour. So this is how these guys work out, because filling in the table gives us an opportunity. Notice, after I filled in the table, I really didn't have to go back to this over and over again. It all came directly from the table. Distance, rate, time. Distance, rate, distance, rate. We used our formula, distance equals rate times time. We used the T equals D over R. That's the one we used. The reason we used it is so that whenever we substituted, we had nothing but the rate left over. Let's pick one out of the textbook. Another one out of the textbook that's really an important one to see is a distance, rate, time one that looks at not just a current thing. So if we look at number 28 out of the text, all right, a truck travels 300 miles in flatland in the same amount of time it takes to travel 180 miles through the mountains.
the rate of the truck in the mountains is 20 miles per hour slower than through the flatlands. Find the rate of the truck in both the mountains and the flatland.
All right, now this is an interesting problem here, ladies and gentlemen, because what we're looking at
When we fill in our table is the same kind of situation, but what makes this interesting is that we don't have a constant
little rate of current. We have the rate of the truck.
which we're looking at. So let's take a look at our two situations. We have the flat land, right, and we have the mountains. We have our distance, rate, time table here. Distance, rate, time. All right, what is the distance in the flat land? All right, the distance in the flat land is 300 miles in the flat land. So the distance in the flat land is 300. What is the distance in the mountains? 180 miles in the mountains. Now, if you ever struggle with where you put these things, ladies and gentlemen, look at your units. We've driven enough to understand that whenever we're given a unit like miles, that's a distance. When we're given a unit like miles per hour, that's a rate. When we're given a unit like hours, that's a time. So here we go. The rate of the truck in the mountains is 20 miles per hour slower than the flatlands. 20 miles per hour slower than through the flatlands. Well, do we know what the rate of the flatland is? No, we don't. So we call the rate of the flatland R. What is the rate of the truck in the mountains? It's 20 miles slower, so we have R minus 20. And the mountains, we already determined that's 180 miles. And then this last thing that it talks about. A truck travels the 300 miles in the what? Same amount of time. Same amount of time. Well, if the time is the same amount, if it's T in the flatlands, it's T in the mountains. So what is this problem asking us to find? It's asking us to find the rates. And if we're asked to find the rates, we use the time. We use T equals D over R. All right, so let's take a look then. So for the flat land, T equals D, which is 300, over R, which is R. And in the mountains, T equals what? T equals 180 over R minus 20. Now, through the method of substitution, this is what we're going to have. 300 over R equals what? 180 over R minus 20. Now, what is it that we have to do to solve this? Do we have to find an LCM, or can we use cross products? I'm glad you said cross products. That's what we have to do. So we have 300 over R minus 20 equals 180 over R. Just out of curiosity, why did you say cross products? You said cross products because we have a single ratio equals a single ratio. And if we have a proportion, which is a single ratio equaling a single ratio, we can use cross products. So we have 300R minus 6,000 equals 180R. Now solving this, we have negative 6,000 equals negative 120. Now where did I get the negative 120 from? I isolated the variable by subtracting the 300R from both sides. So now, we have negative 6,000 over negative 120, equals R. Negative 6,000 divided by 120. And we can very simply, well, we can simplify this. A negative over negative, and then those cancel right there. All right, we get 100 over 12. 100 over 12 is going to give us 50. What did we just find? The cool thing about putting these in a table, what we just found was R. Well, what is R? R is the rate of the flatland. What is the rate of the mountains? The rate of the mountains is R plus, or R minus 1, R minus 20. So, the flatland rate is 50 miles per hour. The mountain rate is 20 miles per hour faster than that. No, it's 20 miles per hour slower than that, sorry. So it's 30 miles per hour. Ladies and gentlemen, that's how we deal with these distance, rate, time problems. Please try to plug them into tables. And remember, if at any point in time you have any questions, don't hesitate to send me an email. Don't hesitate to use your Ask Your Instructor feature of My Math Lab. Because these kinds of word problems, when we're working through them, we have to understand them. We have to read them very carefully. Notice the way that I read through this word problem a moment ago was by carefully looking at it and reading it. This truck, it's traveling. We're dealing with a distance, rate, time problem. We know that. So look at categorizing your problems. You can read it and understand, okay, I'm dealing with a distance, rate, time problem. I'm not dealing with a ratio proportion problem or a cost per item problem. I'm dealing with a distance, rate, time problem. Okay, good. Once you've categorized it, then you can understand the process that you use. All right? Or I'm dealing with a work principle problem. Okay, so I use the work principle as opposed to the distance, rate, time formula. So categorize them. Then after you've categorized them, declare your variables. That's a very important thing. If you look at this entire process of the table right here, that entire process of using that table, that process is a process of declaring our variables. You're looking at R for rate and T for time and D for distance. With work principle, you're declaring your variables as we did a moment ago. You know, you look at the experienced guy versus the apprentice. All of these. So, first, read and understand the problem. Look for any relevant formulas that you have to use and categorize. When you're reading through and understanding the problem, also assign variables that make sense. Unlike the author who continually uses X, I want you to use D and R and T. All right? If you're asked to find, the number of basketballs used by a PE class, use B for basketballs. That way, whenever you solve the problem at the end, you're not trying to figure out, okay, I've got X. What does X mean? If you're using B for basketballs and C for cookies and H for whatever, T for time, D for distance, R for rate. If you're using these variables that make sense, when you get to the end, you'll know what you've just solved for. After you've read it carefully, understood the problem, categorized it, and declared your variables and looked for relevant formulas, after you've done the first step, which is the understanding step, then you move on to the second step, and the second step is to solve your problem. The second step is to solve your problem. Solving may require this substitution, and probably always you'll be using substitution. Once you've done that, then we solve. That's what all this is about. After you solve and check, then you make sure your answer makes sense. Make sure that answer makes sense. For instance, if I solved this thing and I've got 50 and I can't remember what that represents, all right, I might think that that 50 represents miles. No, because in the problem itself it said 300 miles. Make sure your answer makes sense. For instance, if you're asked to find the rate of an airplane and you get 12, does that really make sense? Is an airplane going to travel 12 miles per hour? No, it's not. So make sure that your answer makes sense. And then always state your answer using units. And notice we've used miles per hour because 50 miles per hour is what makes sense because it's a rate. That's it for 7.6. Now I hope that you carefully consider how you look at word problems. The solving of word problems, ladies and gentlemen, this right here, I find that in my experience, students really do not struggle with this stuff. They don't struggle with all of this. All right, that was pretty straightforward. Where does the struggle come from? The struggle comes from translating from the words into usable mathematics. All right, going from here to here. That's where the struggle comes in. So read your problems very carefully and go through that process that I just described. Read carefully, understand what's being asked, categorize your problem, declare variables that make sense, look for any relevant formulas, then you go into your solving. Too often we read through a word problem like we're reading through a Cosmo magazine or a Field and Stream. Read through it carefully, look for important words. Notice the way that I read through it, understanding what's being asked. That's it for 7.6. I look forward to seeing you guys in the next video lecture, 7.7. Again, please don't hesitate to ask me any questions. Email me, go through the instructor resources, whatever you have to do. That's it. Thank you all.